So let's continue for the effect of seepage. This is also under the stresses of soil, effective stress of soil. So the interaction between soils and percolating water has an important influence on the design of foundations and earth slopes. The quantity of water that will be lost by percolation through a dam or its subsoil. So as water flows through soil, it exerts a frictional drag on the soil particles, resulting in head losses. The frictional drag is called the seepage force in soil mechanics, and it is often convenient to define seepage as the seepage force per unit volume. It has units similar to unit weight, which we will denoted as J sub S if the head loss over a flow distance L is delta H. Then the seepage force is given as J sub S is equal to delta H over L. This is the hydraulic gradient I, if you remember, times the unit weight of water. So, or is also equal to I times gamma sub W. So this is the seepage now. This is the interaction between soils and the percolating water. So we have here representation of a figure no nga walay seepage. And this one, the next slide, is a representation of an upward seepage. Actually, they are the same, but kanisha is no seepage. Well, this one has an upward seepage. You have here the inflow of water, then it will flow in here. Then you have here a soil mass in this length now of soil. Then there is an outflow of water. Then the upward seepage, known as the upward seepage, represented by these arrows. So if this is the soil, then you have the weight, the buoyancy. So the force no in the soil mass is buoyancy plus the seepage force. This is for upward seepage. While for the downward seepage, from here, diri ang inflow sa water. So if this is the soil mass in this length, ni flow ang water downward, then ni outflow siya diri. So the seepage force is downward, no? And buoyancy is of course upward. So buoyancy minus the seepage force. So unsa implication ani? The downward seepage, if seepage direction is downwards, then the resultant seepage stresses are in the same direction as the gravitational effective stresses. This is discussed early in the previous topic, diba? Topics. While for the upward seepage, they are in the opposite direction. So the effective stresses, now total effective stresses, is actually equal if the seepage is downward is the buoyant unit weight times the z. This is the distance. Now if you want, or the from the water table to certain distance, for example z, this one kani siya, if this is the soil element, no, plus the iz gamma w, or the unit weight of the water. This is the hydraulic gradient, or the delta H, the head loss divided by the length of the kanang the soil where na ay dito gaagi ang tubig, or is also equal to the buoyant unit weight z times z plus j sub s z, the height, no? in case of upwards, ma-minus siya, no? Buoyant unit weight times Z minus IZ gamma sub W, or gamma prime Z minus J sub S Z. This is for the effective stress. So we'll try to better understand that one in the later example. The effect of seepage on structures. Foundation failures due to piping are quite common. Piping is a phenomenon by which the soil on the downstream sides of some hydraulic structures get lifted up due to excess pressure of water. The pressure that is exerted on the soil due to the seepage of water is called the seepage force or pressure. This is the effects of seepage and effective stresses near a retaining wall. So if this is the retaining wall, there is an excess pressure diri sa upstream. Ang tendency ani mo overturn ni siya diri retaining wall because of the excess pressure diri dapit, no? Due to the seepage of water. Overturn, no, ang effect ani niya. Effects of seepage continuation. In the stability of slopes, the seepage force is a very important factor. Shear strengths of soils are reduced due to the development of neutral stress or pore pressure. So remember, neutral stress is also the same with pore pressures. A detailed understanding of the hydraulic conditions is therefore essential for a satisfactory design of structures. The computation of seepage loss under or through a dam, the uplift pressures caused by the water on the base of a concrete dam, and the effect of seepage on the stability of earth slopes can be studied by constructing a flow nets, which is we already discussed in the previous topics, no? Alright, so water, I think this is an example already. Water is seeping downward to a soil layer in figure. Two piezometers A and B located 2 meters apart, no? Show the head loss of 0.2 meter. Calculate the resultant vertical effective stress for a soil element at a depth of 6 meters shown in figure. So since the seepage is downward, as you can see, there is a seepage downward. So the solution. Okay, for the solution of this one, we are required, no, to determine the resultant effective stress for a soil at 6 meters, no? Remember, if the seepage force is downward, so the total vertical stress is equal to the buoyant force times at certain distance, since this is downward seepage, so you have to add times the hydraulic gradient I Z delta unit weight of the water, no? But at 6 meters, di ba? Between A and B. So meaning the Z here is actually equal to 6 meters. But there is a head loss between A and B, di ba? So between A and B head loss, meaning ang I ni mo ana, remember I is equal to head loss delta H over L. So meaning your I is equal to between A and B, di ba? Ang head loss. So 0.2 over from A to B, kay ang water is from A to B ang direction. Actually, the L should be 2 meters ang L ni mana. So substitute the value, this buoyant force, this is actually this one is gamma sat minus gamma water, no? So that will becomes the total effective stress is actually equal to gamma sat of soil minus gamma water times Z plus delta H over L times Z gamma water. Or if you try to substitute, the gamma sat is given as 18.5 minus 9.81 times Z, because we are after between, no? Calculation elementary soil at a depth of 6 meters, meaning this is the Z, no? So times 6 plus delta H over L, so that is 0.2 over 2 times 6 meters at the Z times 9.81. So this is your effective, what is the answer of this one? Muna siya ang imong effective vertical stress, no? That is the answer for this example problem. So we move on to this quicksand conditions in soil. Alright, so we try to understand this figure, picture. So this is the inflow of water, then the outflow, no? So the total stress of this representation of this figure is that you have the height, no? Alright. Yes, so that is Z1 plus Z2 times unit weight of the water plus Z1 times the unit weight of this soil, no? This is the total stress, no? For the pore water pressure, that is Z1, this one, Z1, I mean, this is Z1, no? So this is Z2 and this is Z1, and na ay Z, what is the seepage force, no, or the effective stress at Z, and this is Z at a certain distance, kana Z. So for the total pressure is, for this one, that is Z1 plus Z2 times unit weight of the water, Z1 plus Z2 times unit weight of the water plus Z1 times the buoyant unit weight at Z1, no? Well, the pore water pressure is Z1 plus Z2 plus IZ times unit weight of water, because naa kay seepage man dire. Naay seepage at Z, no? Naay seepage at Z, which is downward, mo ni siyang plus, no? While in here, Z1 plus Z2 plus H times unit weight of the water. So, and for the effective stress is at this point here, that is Z times the buoyant unit weight minus IZ gamma W. And this one, alright, there is head loss, no? Naay head loss. So the water surface in container B is kept above that of A. by H units. Okay, this is the effect of H units plus H times unit weight. So this arrangement permits water to flow upwards through a sample container in A. This is the sample container. The total piezometric or the pore water head at the bottom of the sample is given by Z1 plus Z2 plus H. This is the difference of height, no, between A and B. Therefore, the pore water pressure U sub Z at the bottom of the sample is Z1 plus Z2 plus H times the unit weight of the water. And the total pressure head at the bottom of the sample is Z1 plus Z2 times the unit weight of water plus Z1 times the buoyant unit weight at the bottom of the water. Okay, this is the condition of the quicksands. Quicksand condition is that kanang inyong makita sa TV nga or sa movie nga kana bitang murag makaagi ka very sandy nga place or very muddy nga area, wala ka balo nga kuan dayto quicksand dayto siya. Then pag maka-enter ka ato, kuan ka ato, malubong ka diretso hangtod nga i-absorb ka niya sa ilalom, no? That is the quicksand condition. The effective pressure at the bottom of sample is therefore sigma prime sub C is equal to sigma C minus the pore water pressure, no? The effective pressure. So, imo lang siyang minus the total stress minus the pore water pressure. The general equation for effective pressure at depth Z is given as this equation indicates that there is a decrease in the effective pressure due to upward flow of water. At any depth Z, the Z times the YB, this is the buoyant unit weight, is the pressure of the submerged soil acting downward, and the ZY sub YB is the seepage pressure acting upward. The effective pressure becomes zero when the effective stress is, or the critical, no, hydraulic gradient, if the buoyant unit weight over the unit weight of the water is equal to the I. So, kung mahimo siyang I, then makancel ang unit weight of the water. Then, the effective stress will be equal to 0. It indicates that the effective pressure reduces to 0 when the hydraulic gradient attains a maximum value, which is equal to the ratio of the submerged unit weight of the soil, submerged unit weight. The Y sub B can be also, or is also known as the submerged unit weight of the soil and the unit weight of the water. This gradient is known as the critical hydraulic gradient I sub C. In such cases, cohesionless soils lose all of their shear strength and bearing capacity, and is visible agitation. And visible agitation of soil grains is observed. This is known as boiling or quicksand condition. So, ang kasagara condition kasagara soil type is the cohesionless soil type. Remember this condition, no? For a quicksand condition, mahimo siyang 0. This is actually the effective stress, di ba? If there is a kanang upward pressure, so mo nang minus. This will be equal to 0. Now, the effective stress will be equal to 0 if the hydraulic gradient will reach its maximum nga ang submerged unit weight, the hydraulic gradient is equal to this ratio of submerged unit weight and the unit weight of the water. So we know that the submerged unit weight, no, this is the submerged unit weight, or the buoyant unit weight. Actually, this is the submerged unit weight of the soil in quicksand condition is equal to this formula. Then hence we have I sub C is equal to this formula gyapon, no? This is important for a quicksand condition, these two formulas. The critical gradient of natural soil deposits can be calculated if the void ratios of the deposits are known for all practical purposes. The specific gravity of granular materials can be assumed as equal to 2.65 critical hydraulic gradients of granular soils. So we have here the different soil type and its void ratios and asya corresponding critical gradient, no? I sub C. Another continuation, no? For quicksand conditions. Quicksand conditions are common in excavations below the groundwater table. This can be prevented by lowering the groundwater elevation by pumping before excavation. No? Quick conditions occur most often in fine sands or silts and cannot occur in coarse soil. So, kung yung matanaw sa movie, katong nalubong, no? Ay, katong ma-observe siya og tao. Siya, fine sands to siya or silts. The larger particle size, the greater is the porosity. To maintain a critical gradient of unity, the velocity, meaning critical gradient equal to 1, no, of unity. The velocity at which water must be supplied at the point of inflow varies as the permeability. Therefore, a quick condition cannot occur in coarse soil unless a large quantity of water can be supplied. Have zones of saturation. The unsaturated zone, this is the zone between the land surface and the water table. So in here, in this figure, this is the, maklaro ba? Alright. And never mind these words, no? Kaya di siya mabasa. This part here, kani siya nga part, this part here, this is actually the unsaturated zone. This is the zone between the land surface and the water table. Remember, the water table is in here, no? Nara diri ang water table. So, this one, this is the capillary, the unsaturated zone. Pore contains water and air, and also called as vadose zone or the zone of aeration. In this part here, this unsaturated zone, this is composed of the nashay contains zone for water and air, this part. So muna siya ang saturated zone. While the saturated zone, pores are completely filled with water, contains water at greater than atmospheric pressure, also called phreatic zone. So this part, this one, this is the saturated zone below the water table, This is the saturated zone. This part, saturated zone. Well, water table, a surface where the pore water pressure is atmospheric divide between saturated and unsaturated zone. Well, the water table, this is actually the line for the water table. This divides the unsaturated zone and the saturated zone. While the zone of capillary rise or fringe, this is the zone immediately above the water table that gets saturated by capillary forces. So this is this distance here. This is the zone of capillary rise. Remember, na atay water table diri na ay actually capillary rise nga mahitabo. So that distance or portion, this is the capillary rise or fringe. So you can see this is the capillary rise. Na siya sa unsaturated zone but nasaturate siya because of the capillary rise from the water table because of the capillary forces. We have categories now for soil water. We have the hygroscopic water, microscopic film or water surrounding soil particles, strong molecular attraction, water cannot be removed by natural forces, adhesive forces. In capillary water, water held by cohesive forces between films of hygroscopic water can be removed by air drying or plant absorption. Plants extract capillary water until soil capillary force is equal to extractive force. Putting point. And we have the gravity water, the water that moves through the soil by the force of gravity. Field capacity, this is the amount of water held in the soil after excess water has drained, is called the field capacity of the soil. Right. I think 3 more slides. Effective stress in the zone of capillary rise. We have the negative pore pressure suction or suction. Below the water table, the pore pressures are positive. In dry soil, the pore pressure is 0. Above the water table, when the soil is saturated, pore pressure will be negative. So, ganina, the capillary rise, katong ganina, this part here, since this is the dry soil, the capillary rise or the pore pressure in this part is actually negative, no? This represented by this one. The height above the water table to which the soil is saturated is called the capillary rise. So in this part, nasaturate ang soil ani. Even though the water table is only in this line, this part, but because of capillary rise, there is upward seepage of water, no? That is why the pore pressure is negative. But the H, this is the unit weight of the water, but the H is actually equal to the height of the capillary rise only. Kani, this is the H sub W, no? This is the H sub W. Then, and this depends on the grain size and type, and thus the size of pores. No, na capillary rise depends on the grain size and type of pores or size. In coarse soils, capillary rise is very small, no? Kung dagko ang soil. In silts, it may be up to 2 meters, and in clays, it may be up to 20 meters, no? So we have here a figure. You have the dry, so meaning the pore pressure is 0. The unsaturated soil, no? Meaning, kung naay capillary rise diri, still the pore pressure is negative, kani, no? And this part here, this is the naay capillary rise na diri, which is your pore pressure is negative gyapon because the water table is only in this part raman. This part here, this is the water table. Sorry for the hiwi nga. This part, no? This is the water table. Kani siya. So, naay capillary rise nga move upward. So, the pore pressure is negative in this part, no? And the saturated part nga ubos sa water table, this is positive pore pressure, no? Positive U. So what is the total stress, no? Muna dayon ang question. Effective stress in the zone of capillary rise. Consider upward flow. I think this is an example. Consider the upward flow of water through a layer of sand in a tank as shown in figure 8.9. For the sand, the following area are given. No? We have the void ratio given and the specific gravity of soils 2.66. Calculate total stress, pore water pressure, and effective stress at points A and B. Where is A and B? This is A, points A and points B, no? Sorry, dili ko siya maklaro. So, this is 1.5, the difference of the height, no? Think 1.5, then the water table is in this portion of the kuan. Na water diha. So, meaning this is already saturated. But, there is inflow of water. Na valve open diri. Na inflow of water diri. So, naa kay seepage pa upward. So, we are required to determine calculate total stress, pore water pressure, and effective stress at points A and B. So, for A, first is, for the solution, the saturated unit weight of the sun is calculated as follows. Remember this formula now for the saturated unit weight, which is given, the specific gravity is given as 2.66 plus the void ratio is also given equal to 0.68. So, substitute, then we have this value for the saturated unit weight, no? For point A, no, in this table, the total stress is 0.7 plus, times 9.81. This is due to poor water pressure nga sa ibabaw, since naman diri ang tubig, na water diri. So, the height is 0.7 plus 1, because this is at A, the location of A, which is 1 from this point. This is already soil particle na, no? Times the saturated unit weight, 19.503, no? And the pore water pressure in this figure at A is 1 plus 1.5 1 plus 0.7. Okay, 1 plus 0.7 plus 1.5 divided by 2. Alright, why is it that 1.5, this is the times 9.81. So, you have here the water, munang 1 plus 0.7 times 9.81 plus 1.5 divided by 2. 1.5 divided by 2. I don't think this is divided by 2. This should be, wala ka dapat divided by 2. This should be 1.5, no? Ito na correct ha. This should be 1.5. Wala kay 2 ani. I don't know the reason nga nang iyang gi-divide og 2. There is difference in the elevation, no? Na kay flow diri, na ay tube diri. Then, due to dili maklaro, I think this is outflow of water, no? So, munang plus 1.5 times 9.81, no? So, I think this is not the answer, no? This is not the answer. Try to solve this one, and this is not the answer because mautro man siya. Wala dapat divided by 2, no? Then, the effective stress is total stress minus the pore water pressure. Then, ma-change ni siya. Kindly correct this one through solving again the whole and all of the example in this lecture notes. Next is, what is the effective stress at point B? So for B, we have 9.81, 0.7 times 9.81 plus 2 times 19.503. So the answer is, itong i-divide ni siya. 1.5. Oh, alright. I stand, I will correct this one. No? Sakto na I divide 2. Okay. Na I divide 2 because, yes, this is C page, no? Na I C page. So, ang nahitabuan ni, this is, diretso ra magud niya, di ba? This is actually, this one is delta H over L times Z times unit weight of the water ang kani. So delta H, this difference in the head loss, which is 1.5 divided by L, this is 2, no? This is L, height of the soil profile, or L. Mo ni siya. Sakto to siya, no? Sakto. The answer is 24.03 and effective stress is total stress minus the pore water pressure 2.34, no? Then for the point B, that is 0.7 times 9.81 plus 2 times the saturated unit weight of the soil, which is equal to 19.503. So the answer is 45.873. And 4 point. For the pore pressure, for the pore pressure at point B, we have 2 plus 0.7 plus 1.5. Alright, I think this is 2 plus 0.7 plus times 2. Okay. Alright, yan gidiritso. This is times 2 times 9.81. Okay. So, ang nahitabuan ni, wala na siya, ha? Wala na siya. Hindi siya mao. Ang nahitabuan ni, this is actually equal to the figure. This one. 0.2 plus 2. Kaya naman diri ang D. That is 0.2. 0.7, no? 2 plus 0.7. So, kani siya. Okay ni siya. Kaya at kuan man. Times 9.81. Siya dapat kani. Times 9.81. Plus, the capillary rise, the seepage force equal to 1.5. Ay, equals man nun. This should be equals plus 1.5 divided by 2 because this is delta H, no? Kani siya, this is still kani siya, delta H over L times Z. Times Z, which is, the Z here is still 2 man, no? Kay at point B man ka, at point B. So, times 2 times the unit weight of the water, which is 9.81. Munang nahitabo. So, munang cancel out ning 2 dire. And so, for this one, the answer is 41.873. 202. Then, total stress minus the pore water pressure, the answer is, for the effective stress at point B is 4.671. No? The hydraulic gradient I, which is equal to this one, delta H, no, over L is equal to 0.5. Thus, the seepage force per unit volume can be calculated as, okay, the seepage force, no, this is the seepage force, this one, per unit volume is this answer. For letter B, what is the upward seepage force per unit volume of the soil? So try to solve again now the example, and for mastery, and also for this not to this is Z, no, delta H over L times Z times the unit weight of D, and this is the end of the the lecture. Kindly try to watch and study this lecture for this topic, no? The effective vertical stresses in soils.